Hello folks, and welcome to this lesson on transition metals. By the end of this lesson, you should be able to describe and explain the properties of transition metals and explain the nature of coordinate bonds within a complex ion and deduce relevant charges. Now, you've probably been aware of transition elements for quite a while now, from being told earlier on in your educational career that, transition elements are a little bit special. They're in here, but we're not really going to talk about them right now. And you've also encountered them and you know a little bit more about them, particularly around that electronic structure. Now let's talk about how that structure is going to affect many of the different properties of transition metals. Now, first off, let's talk about the definition of a transition element. I know I keep on going between transition element and transition metal, but the thing is that they're all sort of in the same place and all of them do happen to be metals, and so you're going to hear me go between them pretty frequently and pretty interchangeably. Right, so transition elements are elements that form at least one stable ion with a partially filled d subshell. Now, this makes things interesting because up until now you probably thought that all of these in this D block of the periodic table were considered to be transition elements, but that's not actually the case. They don't go all the way. If we take zinc, for example, the last bit of the electron configuration of zinc is 4s2 and then it's 3d10. The only stable cation that zinc makes is that 2+, where you end up having that d orbitals all being completely filled. So these don't actually count. So the first big thing that makes transition metals different from the other metals is the fact that you can have multiple oxidation states. And a lot of this has to do with that whole 4s and 3d have very similar energies. Sometimes one counts as higher than the other, but they are very similar to each other. This all leads to the fact that they can have multiple oxidation states. Now let's take a look at the transition metals, or that D block, in that fourth period. Now from here, we know that zinc is in a transition metal. Another one that's sort of iffy is scandium. If you take a look at scandium, the only stable ion that it has a charge of 3+, which means that there aren't actually any electrons in that d orbital. So you probably wouldn't consider scandium to be a transition metal either. Now, something that you're probably going to notice is the fact that most of these transition metals all have a charge, or all have a stable ion that has a positive 2 charge. Now, with those ones, those are all of those 4s electrons being taken away, and that's how you get that +2 charged stable ion for all of these. For most of these. At the end of the day, part of what's going to make certain ion charges more or less possible or more or less common in specific transition metals is going to depend on those ionization energy values. So consider, is there electron shielding that's going to be a little bit different? That's going to make things change a little bit. Are we looking at a case where you actually have this sort of a situation as opposed to this one, where here if you were taking out an electron, you would be taking it out of this particular subshell, and therefore there is that electron repulsion that happens, which would make that ionization energy a little bit lower, and so on and so forth. So let's move on to talk about a few other properties of transition metals. Now, one of the big things is going to be the fact that when we're dealing with delocalization or delocalized electrons in transition metals versus other metals, is that those d subshell electrons, they actually count towards delocalization. So that means you have a bigger pool of electrons as opposed to something that's in the S block. In your S block, you can only have 1 or 2 delocalized electrons per atom because that's where they are in the periodic table, but with your transition metals, there are so many more that you can use, which means that you can have bigger attraction between the nuclei of your metal and the delocalized electrons. So that means a lot of those metallic bonds are going to be stronger compared to something that's in that S block, like potassium or calcium. So this means that you're going to have a higher melting and boiling point, the density is going to be higher, bigger attraction, everything is going to sort of shrink down because of that attraction, and you're also going to have higher electrical conductivity. There are many reasons for why you wouldn't use something like calcium for wires. One of the big ones being the fact that it actually reacts with oxygen and water really readily, and causes a bunch of explosions. That's going to be one reason why you wouldn't use that to make wires. The other thing is that it's not going to be as electrically conductive than something like copper, which is at that end of your periodic table, even within the transition metals. Copper is really good because it has so many delocalized electrons to work with, even compared to things that are in the same group. Magnetism is another property that you see in transition metals, but you don't really hear quite a bit about in terms of something like the S-block metals. Magnetism happens because you can have unpaired electrons in that D block. And because of the unpairedness of it, you get magnetic properties. Now, when we're drawing our orbital diagrams, there is a reason why we draw those individual electrons as arrows. That's because your electrons spin. And if you have taken physics, you probably know that when you have something like an electron that's a charged particle that spins, it creates a magnetic field. Now, if you had an element or an atom that had this particular set of electrons, you can see that there's quite a bit of spinning. All of them are spinning in the same direction, and so that means that you have quite a bit of a magnetic field that forms because of those electrons. Now, if we add another electron in here, it's not going to spin in the same direction, it's going to spin in the opposite direction, and that means that the magnetic field that's created by the first electron is being cancelled by the second electron. So more unpaired electrons are going to give you a stronger magnetic property. The more paired ones you have, that's going to give you a weaker magnetic property. Something that has stronger magnetic properties is referred to as being paramagnetic. Something that does not have strong magnetic properties is referred to being diamagnetic. Those two particular terms are not very important at this point. Now, transition metals can also be used as catalysts. If you remember back with those standard hydrogen electrodes, you had a catalyst, or you had an inert electrode of platinum or palladium that is the site for that half reaction to happen. Now, this is possible because of the fact that you can have variable oxidation states with these metals, and also because of the ability to form complex ions with other substances that are in your solutions, which we will talk about in a different lesson. That's it for this lesson. I'll see you next time.